Hello guys, hope you are doing well. In today's session, I will be talking about the chapter 3. In chapter 3, we have two sections. The first section will be talking about the aqueous solution and the concept of pH. And the second section will be talking about the determining pH and titration process. In the first section, we will be calculating the pH, pOH, hydronium, hydroxide of the solutions through different types of questions. And then let us start with the first section, guys. Probably we discussed about the ionization and dissociation in the previous chapters. We have at the beginning of this section, we have a term we call as the self-ionization of water. The water molecules, they have a tendency which is unique among all the solvents. They can donate proton or transfer proton in between two molecules of water to produce hydronium and hydroxide, and we call that as the self-ionization of water. So the self-ionization of water is what, guys? Is the reaction of two water molecules to produce hydronium and hydroxide ions. As it's written, guys, the H2O reacts with the H2O to produce hydronium and hydroxide. In this reaction, one of the H2O is going to be the donor of the proton and becomes a branched lauric acid, and the other one acceptor of the proton, which is the branched lauric base, and produce a hydronium, which is a conjugate acid of H2O, and hydroxide, which is a conjugate base of the H2O as well. So this process lets the distilled water or the pure water, which will be solving that question, and it appears in ministerial exam question as well, said distilled water contains which of the following? So guys, distilled water contains hydronium, hydroxide, and H2O as well. All of them is the correct answer for that question. Why? Because of having self-ionization between two molecules of water. One is going to be act as the branched lauric acid, the other as the branched lauric base. Simply, that's a self-ionization of water. In terms of conducting electric current, guys, water, pure water, is extremely weak electrolyte. So we have to know that it's extremely weak electrolyte, as I have written here. Why is extremely weak electrolyte? Because the self-ionization of water is not favorable process. We mean it's not in a strong, in the scale of the strong acids and strong bases to produce the ions. That's why the water molecule, they do not form the ions as the strongest, and the existence of the hydronium and hydroxide in the pure water is not a lot. That's why it's extremely weak electrolyte. Guys, for the term of the concentration, we use a bracket like this, and then for that represents what, for example, a bracket of hydronium means the hydronium ion concentration, and this concentration we mean in mole per liter, which is the molarity equals the mole per liter. We'll be measuring the concentrations in this section in molarity, not in molality. Okay. Guys, we have another term we call as the constant ionization of water, or ionization constant of water. Ionization constant of water, which represents by Kw. Guys, what the Kw represent? It represents of always in the water solution we have an amount of hydronium and hydroxide. An amount of hydronium and hydroxide. Sorry guys. Amount of hydronium and hydroxide. The Kw represent what? Represent the degree of ionization of water. The degree of ionization of water, if ionized more, that represents or releases more ions, more hydronium and hydroxide to the solution or to the medium. If ionization degree reduce the concentration of the ions. And the Kw represents the degree of ionization of water. And this degree of ionization of water can be calculated through an equation. In this section, guys, we have got 6 equations. This is the first equation, which Kw is equal to the multiplication of hydronium and hydroxide concentration. Here we multiply the hydronium and hydroxide concentration and we'll get the Kw. Why? Because, as I told you, it represents the constant ionization of water, represents the ionization degree of water. Through the existence of ions, we will be able to determine the ionization degree of water. And guys, at 25 Celsius, 3 values should be memorized, or you have to memorize these 3 values: the hydronium concentration, hydroxide, and Kw as well. Hydronium and hydroxide at 25 Celsius, they are equally existing and is equal to, both they are equal to 10 to the power minus 7 for each of them. Kw is equal to the multiplication of these two, so 10 to the power minus 7, multiply 10 to the power minus 7, you'll get a 10 to the power minus 14, 1 10 to the power minus 14 for the Kw must be memorized, because sometimes the questions will be solving the hydronium, and the hydronium is given, maybe given and required to calculate the hydroxide. Through the Kw will be able to calculate the hydroxide, or vice versa, the hydroxide is given, calculate the hydronium. So the Kw, hydronium and hydroxide at 25 Celsius must be memorized. In any other degrees, we are not required to memorize the values of hydronium and hydroxide and the Kw as well. Guys, the ionization of water increase as temperature increase. We have got 4 relations. I would like to tell you those relations, guys. The first one, at any given temperature, Kw is always a constant value. And from this table, as the temperature increases from 0 to 50, what happens to the Kw increases as well. So we can say the first relation is what? Increase in temperature. Kw increases with increasing temperature and changes with changing temperature, directly proportional or proportionality. And the next one, guys, the hydronium and hydroxide. Temperature is directly proportional with hydronium and hydroxide. Why? Because, guys, as temperature increase, that provides a better medium to the water molecules to ionize. So it increases the ionization. This is the second relation. How the ionization of water or the other molecules, acids, increase? By increasing temperature, we can increase their ionization. Guys, as the ionization of water increases, what will be the product of the ionization of water? The 2 water molecules, they self-ionize. Of course, hydronium and hydroxide. So we can say the third relation is what? As temperature increase, the concentration of the hydronium increase. The fourth relation, temperature increase, concentration of hydroxide increase as well. But guys, the hydronium with the hydroxide, if we take the relation in between these two, they are inversely proportional, because as the hydronium increase, hydroxide must decrease to get the same value of Kw, because Kw is equal to hydronium concentration multiplied to the hydroxide concentration. Whenever the relation between two varied quantity is multiplication, that represents what? Represent they're inversely proportional with each other. Inversely proportional with each other. To get a constant value, decreasing this must increase the other to get the same result of Kw. So we have to know that temperature increase Kw, ionization of the water, and then ionization degree, and then hydronium and hydroxide. But the hydronium is inversely changing with the hydroxide. Here we have the figure 2, guys. It's about the dry ice and sodium peroxide. In part A, stated that the addition of dry ice, carbon dioxide, to water increased the hydronium. How it increased the hydronium? When, guys, carbon dioxide, which is the dry ice, reacts with H2O, the result is the H2CO3, carbonic acid. So you know that the carbonic acid formation of a carbonic acid in a medium increases the hydronium concentration. So addition or reaction of dry ice with water increases the hydronium and decreases the hydroxide in the medium and increases the acidity of the medium. But as shown in the part A, in part B, guys, the sodium peroxide Na2O2, when it reacts with the H2O, we will get what? We'll get the sodium hydroxide and oxygen gas. So the sodium hydroxide here is base. You know that is a strong base. So formation of sodium hydroxide in a medium, that means increases the hydroxide concentration as it's given here, and then decreases the hydronium is the same. So the sodium peroxide here increase the alkalinity, but the dry ice increase the acidity of the medium, we mean the hydronium. In terms of acidity and alkalinity, we have got three types of solutions, guys. The acidic solution, basic solution, and the neutral solution as well. We will be talking about the differences of each of those solutions, how to differentiate between them, because we may be confusing due to of having the values of hydronium and hydroxide for the solutions. But here we will represent how to differentiate between them. Simply, guys, the neutral solutions are those solutions that the concentration of hydronium and hydroxide is equal in the solution, in the medium. So whenever the concentration of hydronium and hydroxide is equal, the solution becomes a neutral solution. How to form an acidic solution? The acidic solution is different from the neutral solution in that the solution contains a higher concentration of hydronium because of existing a higher acid in the medium. So the acidic solution is a solution in which the hydronium is higher than the hydroxide, so the solution becomes the acidic. And the basic solution is just the opposite of the acidic solution, which the hydronium is lower than the hydroxide and the solution becomes basic. So guys, we can say another statement that for the neutral, in terms of values, the hydronium and hydroxide are equal, and both they equal to the 10 to the power minus 7. At 25 Celsius, of course. But for acidic, the hydronium must be higher than that value, 10 to the power minus 7. For basic, the hydroxide must be higher than 10 to the power minus 7. We will be explaining more in the coming pages about this. So guys, an example here, a solution containing 10 to the power minus 4 hydroxide. What do you predict about the property of that solution? Of course, when the hydroxide is higher than 10 to the power minus 7, which 10 to the power minus 4 is what is basic, because hydroxide is higher than 10 to the power minus 7. Calculating hydronium and hydroxide through the concentration of the acids and bases. Here I have provided the notes in order to know how to convert the concentration of the acids to the hydronium and hydroxide. But here we will be solving only for the strong acids and strong bases. At the end of the section, we will be talking about the weaks because they are partially ionizable or dissociable compounds. We are not able to determine the hydronium and hydroxide as the strongest. Guys, if we have full possibilities of questions, if the strong base 1 hydroxide concentration is given, the concentration of strong base group 1 plus hydroxide, lithium hydroxide, sodium hydroxide, potassium hydroxide concentration is given, directly the concentration of the base is equal to the hydroxide concentration. So it's what directly we can obtain what the concentration of the hydroxide, which is equal to the strong bases concentration. But if 2 hydroxide is given, so let me provide for the 1 hydroxide, guys. NaOH, when it dissociates, it will produce Na positive and OH negative. So it's balanced equation. 1 mole of NaOH dissociated produce 1 hydroxide. So any amount of this, the mole ratio, will produce the same amount of the hydroxide. That's why if any amount of this acid, this base, 1 to the power minus 5 is given, completely dissociate to form 1 to the power minus 5 hydroxide and also 1 to the power minus 5 Na as well. So here the hydroxide is directly equal to the concentration of the strong base. For the second, if group 2 hydroxide is given, like calcium hydroxide for example, guys, produce Ca2 positives and 2 hydroxide negative. This is for balancing. Guys, if an amount of this is given 1 to the power minus 5, as you can see here, 1 calcium hydroxide dissociated to produce 2 hydroxide. So the concentration of hydroxide is twice as the base which is given. It will be 2 multiply 1 to the power minus 5. So 2 to the power minus 5 will be the concentration of hydroxide. But still Ca is 1 to the power minus 5. Why? Because we have got 1 mole of Ca formed in the solution. So guys, this equation I have derived it as an equation. Whenever the concentration of a strong base 2 hydroxide is given, multiplied by 2 to get the hydroxide concentration. Multiply by 2 to get the hydroxide concentration. Let us talk about the bases, the acid, sorry. If the acid is given, for example, monoprotic acid HCl plus H2O will produce hydronium plus Cl negative. Guys, 1 mole of HCl ionizes to produce 1 mole of hydronium and 1 mole of Cl. So any amount 1.2 10 to the power minus 8 HCl will produce 1.2 10 to the power minus 8 hydronium, 1 10 to the power minus 1.2 10 to the power minus 8 Cl as well. So completely we can say it's ionized and produce the exact amount of hydronium. So we can represent the relation as that. A strong monoprotic concentration is given. The hydronium is equal to the concentration of the acid. But if, guys, a strong diprotic is given, H2SO4, H2SO4 plus H2O will produce hydronium plus HSO4 negative, and then HSO4 negative will produce hydronium and SO4 2 negatives. Guys, here we have got 2 hydroniums. So 2 protons exist. The two proton reacts with 2 H2O to produce 2 hydronium. So the H2SO4 has concentration must be multiplied by 2 to get the concentration of the hydronium. Why? Because it's diprotic. Simply, if concentration of strong base of group 1 is given, directly hydroxide is equal to their concentration. If group 2 is given, multiplied by 2 equal to the hydroxide. If diprotics is given, multiplied by 2, you'll get the hydronium, diprotic acid. If monoprotic acid is given, directly is equal to the concentration of the hydronium. Guys, in order to convert for example, here we have got NaOH. NaOH 1 10 to the power minus 2 is given. So directly we will get 1 10 to the power minus 2 of hydroxide. How to convert this into hydronium? Of course, by using the Kw equation which we studied above, is equal to the hydronium is equal to Kw divided by the hydroxide. 10 to the power minus 14 divided by 10 to the power minus 2, you'll get 10 to the power minus 12 molarity of hydronium. And then, as you know, the hydroxide is higher than 10 to the power minus 7. That's why the solution is basic solution. Sorry, guys. Let us solve for an acid. We solve it for a base. The acid here is HCl. HCl is monoprotic. The concentration of HCl is given 2 10 to the power minus 4. So directly this is equal to the hydronium concentration. We calculated the hydronium concentration, which is equal to 2 10 to the power minus 4, and the hydronium is higher than 10 to the power minus 7. So the solution is what? Is acidic. How to convert this hydronium into hydroxide? Hydroxide is equal to Kw divided by the hydronium. 10 to the power minus 14 to 10 to the power minus 4 is equal to 5 10 to the power minus 11 molarity. So the Kw is equal to hydronium multiplied hydroxide at constant temperature. The hydronium increases, the hydroxide must decrease in order to get the same value. We talked about that relation, guys. Here we have got a sample problem in our book. Let us solve the sample problem. A 1 10 to the power minus 4 HNO3 is given. So calculate the hydronium, calculate the hydroxide. Simply, guys, HNO3 will produce the same amount of the hydronium. So that hydronium is equal to that amount. 10 to the power minus 4 is higher than 10 to the power minus 7. That's why it's acidic solution. And then to calculate the hydroxide, 10 to the power minus 14 divided by 10 to the power minus 4, you get 10 to the power minus 10 molarity of hydroxide. The practice, here we have got the practice, it's for monoprotic. Let us solve somehow for the others, guys. This is for 2 hydroxide base. 2 hydroxide base. The 2 hydroxide base, here 1 10 to the power minus 4 is given, produces twice hydroxide as itself, so it will be 2 10 to the power minus 4. So the hydroxide is equal to 2 10 to the power minus 4, which is higher than the hydronium and higher than the 10 to the power minus 7 and is basic. How to convert this into hydronium? By dividing the Kw into the hydroxide, you'll get the value of the hydronium. Guys, if instead of one of the acids here is given, instead of them is, for example, instead of this is H2SO4. So the H2SO4 will produce twice hydronium as itself, and if it's H2SO4 will produce 2 10 to the power minus 3 hydronium. So the hydronium will be twice as the H2SO4's concentration, and then you'll be able to use the value of the hydronium to calculate the hydroxide through the Kw. In this part, we learn how to calculate the hydronium hydroxide from the concentration of the strong acids and strong bases through those above notes, the four equations which I have derived, and by using the Kw we will be able to convert the hydronium to hydroxide and vice versa. Let us talk about the pH scale, guys. Probably you may have studied in the previous stages that the pH scale is a scale of measurement which uses to measure the acidity and alkalinity of the solutions, and this scale is much easier to be used for measuring the acidity and alkalinity of solutions. Because expressing acidity or basicity in terms of the concentration of hydronium and hydroxide can be hard because the values tend to be very small. Having those small values of hydronium and hydroxide, we will not be able easily to understand the acidity and alkalinity of the solutions. A more convenient quantity, which called the pH, guys, can be used to indicate the hydronium ion concentration of a solution. So the pH is what? Defined as the negative logarithm of the hydronium ion in the solutions. The pH refers to what? To the power of hydronium, power of hydrogen or power of the proton. This is the power of the hydrogen. Represents what? Represents the existence of the hydronium in the solution. The second equation, I told you we have got 6 equations. We talked about Kw, which was the first. The second equation is how to calculate the pH through the hydronium concentration. The pH is equal to minus log of hydronium concentration. This must be memorized, guys. For example, guys, here we have got hydronium is equal to 10 to the power minus 7. How to find simply the pH of this solution? We have to say minus log of 10 to the power minus 7, and the pH is equal to 7. In the calculator, simply just press the minus and then log, open the bracket, write the number, and results the pH of the solution. Besides the pH, guys, we have another quantity which we call as the pOH. As the pH was the power of hydrogen, the pOH is the power of the hydroxide. So pOH is what? Is the power of hydroxide. The power of hydroxide is used to determine the alkalinity and acidity as well as the pH. But directly from which value we can calculate the pOH? From the hydroxide concentration. So it's defined as the negative of the common logarithm of hydroxide concentration, and this is the third equation which must be memorized to calculate the pOH of the solution through the hydroxide concentration minus log of the hydroxide. Here we have got an example. If the hydroxide concentration is 10 to the power minus 7, how to convert this to pOH? Simply minus log of 10 to the power minus 7 represents the pOH of 7. That means the solution is neutral. The pH as well is 7, means neutral. We have another equation, the fourth equation, guys. So we studied Kw, we talked about Kw, the equation of calculating the pH, determining the pOH, the third, and then here we will be talking about the pKw value. Guys, remember that the values of hydronium and hydroxide are related by Kw. The negative logarithm of Kw at 25 Celsius is equal to 40. And what's the negative logarithm of Kw is pKw. So pKw is equal to negative logarithm. Instead of Kw, we can write down hydronium multiply the hydroxide. Why? Because this is equal to the Kw value. And pKw is equal to minus log of 10 to the power minus 14 at 25 Celsius, of course. And pKw is equal to 40 at 25 Celsius. The fourth equation can be stated as that pH plus pOH always is equal to 40. pH plus pOH always is equal to 40. And guys, unlike the Kw, pKw is inversely proportional with temperature. pKw is what is inversely proportional with temperature. Means as the temperature increases, the pKw, which is negative log of the Kw, reduces, but the Kw increases. So temperature has an inverse proportionality with the pKw, but a direct proportionality with the Kw. And the equation can be represented as what? pKw is equal to pH plus pOH as well. Instead of pKw, we can say 14 always is the number. Why? Because the scale of pH scale ranges between 0 till 14. So the summation of the pH and pOH in this between all must be 14, not more than 14. Guys, I will be providing direction or some information on this scale. The scale must be used to determine the pH, pOH, hydronium and hydroxide. 0, I will highlight 0, 7 and 14. The least, the midpoint and the highest point on the scale. Prior to that, as I told you, the pH scale is a scale of measurement that uses to measure the pH of the solutions, determining the acidity and alkalinity of solution through an easier method, which is the numbers, the whole numbers, instead of small numbers. Guys, approaching toward 14 increases three quantities. First, increases the pH of the solution. Second, increases the hydroxide concentration in the solution. Third, increases the alkalinity of the solution. But at the same time, guys, it decreases three other quantities. Decreases the pOH, decreases the hydronium concentration, decreases the acidity of the solution. And that's true for the reverse process, guys. For the reverse process. As we approach towards 0, three quantities of pOH, hydronium concentration, and acidity increase. But three other quantities of pH, hydroxide concentration, alkalinity reduce. This must be known in order to determine or to solve the types of questions. For example, may I ask you HCl, H2O, HNO3, or we can say NH3 or NaOH. Which of them has the highest alkalinity? NaOH is much closer towards 14. Which of them has the highest acidity, the strongest acidity? HCl. Which of them the hydronium is higher than the hydroxide? In HCl concentration solution. Which of them the hydronium lower than the hydroxide in ammonia and NaOH? In which of them the hydronium is equals the hydroxide in H2O solution? That we can answer the questions based on the scale, the pH scale in this figure. So it's important to know how the hydronium hydroxide pH, pOH, alkalinity, acidity changes by approaching toward the 14 and approaching toward the 0 on the scale of pH scale. This table, table 4, summarizes the properties of acids, alkaline, acid, basic, and neutral. Guys, simply in the solution of acids, or we can say neutrals, in neutral, the hydronium concentration is equal to the hydroxide. As they are equal to the hydroxide, and both they are equal to 10 to the power minus 7 at 25 Celsius, 10 to the power minus 7 at 25 Celsius, and then equalize, if the hydronium and hydroxide are equal, the pH and pOH also equal. So hydronium, hydroxide, pH and pOH, they are all equal. The pH and pOH of the neutral solution is 7. But for the acid, guys, the hydronium is higher than the hydroxide. And we can say the hydronium is higher than 10 to the power minus 7, but hydroxide is lower than 10 to the power minus 7. In terms of pH, the acids, they have a lower pH than 7. A lower pH than 7. The acids, they have a higher pOH than 7. A pOH higher than 7. And then simply we can say the pH is lower than the pOH. But for the bases, it's just the opposite, guys. The hydronium lower than the hydroxide concentration. Hydronium is lower than 10 to the power minus 7 molarity. This is all values at 25 Celsius, of course, guys. Hydroxide higher than 10 to the power minus 7. pH higher than 7. pOH lower than 7. And simply we can say pH is higher than pOH for alkaline solutions. The relations, guys, these relations are very important. pH, pOH, pKW are inversely changing with temperature. pH, pOH, pKW are inversely changing with temperature. Second, hydronium, hydroxide concentrations with Kw and ionization are directly with temperature. We talked about this and I mentioned it again in order to summarize it. pH, guys, is inversely with the pOH and hydronium. So a high hydronium means a low pH. A high pH means a low pOH. pOH is inversely with the hydroxide and pH as well. So pH inversely with the hydronium, pOH inversely with the hydroxide. But pH is directly proportional with the hydroxide. A high pH represents a high hydroxide concentration, and pOH is directly proportional with the hydronium. A high pOH of a solution represents a high hydronium concentration of the solutions. When an acid is added to the solution, the hydronium concentration increases because there are an excess of hydronium ion. Some of the hydronium reacts with the hydroxide and consume the hydroxide and reduce the hydroxide concentration, but still the hydronium and hydroxide must reach to a point to be equal to the Kw value at 25 Celsius, which is 10 to the power minus 14. Guys, let us calculate the pH and pOH through the hydronium and hydroxide. So far we have discussed about 4 equations. The Kw equation, which is equal to hydronium multiplied the hydroxide. The pH solution can be calculated through the minus log of hydronium. The pOH can be calculated through the minus log of hydroxide, and pKw is equal to the pH plus pOH, which are equal to 14 for the medians. Let us calculate the pH from the hydronium concentration. How we can calculate the pH from the hydronium concentration? Simply, whenever the hydronium concentration is given, or if it's not given, the acid or the base concentration is given, we will be able to convert to the pH and pOH hydronium hydroxide. In this question, the given quantity is the concentration of sodium hydroxide, which is 1×10⁻³ The unknown quantity is the pH of the solution. How to calculate the pH? Of course, we can calculate pH through the hydronium or through the pOH. So both possibilities can be done. First, you can calculate the hydronium. Hydronium is equal to this value of the NaOH. As I told you, this is the group 1 metal with the hydroxide. Directly, its concentration is equal to the concentration of hydroxide. And then this hydroxide is given by using the Kw value. You can calculate the concentration of hydronium, which is equal to 1×10⁻11 in this case. So the hydronium is equal to 1×10⁻11, and pH is equal to minus log of 1×10⁻11 and is equal to 11. The pH of 11 represents a high alkalinity value, and the pOH is equal to 3 in this case. Why? Because pH plus pOH must be equal to 40, and pOH is equal to 14 minus 11 is equal to 3. So the pOH of the solution is equal to 3. That's why it's a basic solution, because pH is higher than the pOH. Another practice, guys, here we have got several other practices. The A part, B and C, D. The A, the concentration of HCl is given. Directly, this is equal to the hydronium, and then take the minus log of that hydronium, you'll get the pH, and the pOH is equal to 14 minus 3 is equal to 11. For the second one, B, 10⁻⁵ HNO3, this is the concentration of the strong monoprotic acid. Directly is equal to the hydronium, and then as the hydronium is known, take the minus log of the hydronium, you'll get the pH of the solution, which is 5, and pOH of the solution is equal to 9. Part C, guys, so concentration of NaOH is given. That will be the hydroxide concentration directly, and then through using the Kw you can calculate the hydronium concentration, and then hydronium concentration is equal to 10⁻⁻10, the pH is equal to 10, and the pOH is equal to 14 minus 10 is equal to 4. That's the alkaline solution. KOH, the same, guys. KOH, its concentration is equal to hydroxide, the same as the part C, the same procedure. You can calculate the hydronium, hydroxide, pH, pOH of the solutions through the given quantities of the acids and bases. Here we will be solving what? Using a calculator to calculate the pH from hydronium of the solution, guys. Guys, what's the pH of a solution if hydronium is equal to 3.4 10⁻⁵? Simply take by calculator, take the minus log of the hydronium, you'll get the value of 4.47. Unlike the other values, it's a decimal value, it's not a whole number, and the pOH is equal to 14 minus 4.47, which is equal to somehow 9.53. 9.53 will be the pOH of the solution. What's the pH of a solution if the hydronium is equal to 6.7 10⁻⁷? Take the minus log of that value, you'll get 3.17, and then the pOH is equal to 14 minus 3.17 and is equal to 10.87 somehow the pOH of the solution. This can be done through the calculator, has no any difference with the other type of questions. Strontium hydroxide concentration is given. Calculate the pH. How? First of all, the strontium hydroxide will produce twice hydroxide. That's why the concentration of hydroxide is twice as its concentration. And it will be 4 10 to the power minus 2. And how to convert this to the hydronium? By using Kw. Kw divided by the hydroxide, you get the hydronium concentration, and then take the minus log of that hydronium, you get the pH of the solution, which is 12.6. Or second way can be used. Second way, from the hydroxide, you can calculate pOH and then subtract the pOH from 14. You will be able to calculate pH. The same value should be resulted in both processes, in both ways. The pOH is equal to 1.4 from the above, then 14 minus 1.4 is equal to 12.6, which is the pH of the solution. What if the hydronium and hydroxide are required and the pH and pOH are given? We have two other equations. We studied 4 equations. I told you we have got 6 equations in this section to solve all types of questions. The 2 other equations, the 5th one is to calculate hydronium, through the pH of the solution. Hydronium is equal to 10 to the power minus pH or antilog of minus pH. Hydroxide concentration is equal to 10 to the power minus pOH or antilog of minus pOH. How to write the antilog? Guys, in your calculator, press shift and then log, shift, log, and then open a bracket minus the number, minus pH, minus pOH. For example, minus 2, minus 3, minus 5 results the hydroxide or hydronium of the solution. That's how we can calculate, we can use the calculator. Shift, then log, minus, open a bracket, minus the value. If it's for pH or pOH, both the same. Antilog of minus pH, you'll get the hydroxide. Antilog of minus pH, you'll get the hydronium of the solution. Let us practice questions, guys. Here we'll be practicing how to calculate hydronium and hydroxide through the pH and pOH solution. Guys, pH is equal to what? Here is equal to 4. So simply the 1 10 to the power minus pH is the equation can be used. 1 10 to the power minus 4 is the hydronium concentration, and then hydroxide can be calculated. 1 10 to the power minus 4, the 1 10 to the power minus 14 kW divided by this value, you'll get 1 10 to the power minus 10 of hydroxide concentration, and then from that we can calculate the pOH as well. pOH is equal to 14 minus 4, 10. A solution of pH of 4 is acidic. The answer of 1 10 to the power minus 4 is greater than 1 10 to the power minus 7, of course, because hydronium is higher than 10 to the power minus 7. It's the acidic solution. We have got a sample problem here, guys. The pH of a solution is measured and determined to be 7.52. 7.52. So simply hydronium is equal to what? 10 to the power minus 7.52 results what? 3 10 to the power minus 8. Why? Because the power cannot be written as a decimal. That's why take the antilog of the same number, you'll get the number that has a whole number as the power. And hydroxide from the Kw can be calculated as well. The pH of 7.52 is higher than 7, and its basic is slightly greater than pH of 7. This means that the solution is slightly basic or alkaline solution. Let us practice more questions, guys. If a pH of a solution is 5, what's the hydronium concentration of this solution? 10 to the power minus 5. Why? Because that's the equation. 10 to the power minus 5. pH is equal to 12. What's the hydronium? 10 to the power minus 12. That's the practices. What's the, if the pH is 1.5, calculate the hydronium and hydroxide of the solution. Hydronium and hydroxide of the solution. Simply take the antilog of that, you'll get 3.1, 10 to the power minus 2, and then divide the Kw, throw the hydronium, you'll get the value of hydroxide, which is 3.2, 10 to the power minus 30. The pH of an aqueous solution, the practice for, is 3.67. Determine the hydronium of the solution. 10 to the power minus 3.67, you'll get a value of 2.13, 10 to the power minus 4. So guys, for the questions, to solve the questions, if any value of the acids and bases given, you'll be able to calculate the hydronium, hydroxide, pH, pOH. Is a chain. There is a chain between these equations. These 6 equations are they form a chain of 6 rings. 6 rings means the 6 equations. Knowing one of the values, if you know hydroxide, you will be able to calculate hydronium, pH, pOH of the solutions, and as well for the others. The section review, guys, calcium hydroxide solution has a pH of 8. Determine the following for the solution: hydronium, hydroxide, and concentration of calcium hydroxide. The pH, guys, is 8, which is given. So the pH can be converted to the hydronium directly, and then the hydronium is equal to 10 to the power minus 8. How about hydroxide? 10 to the power minus 14 divided by 10 to the power minus 8, you get the 10 to the power minus 6, which is the hydroxide concentration. And guys, as the hydroxide known, you will be able to calculate the base solution, the concentration of the bases. The hydroxide in calcium hydroxide is twice as the calcium hydroxide. 1 10 to the power minus 6 must be divided by 2 to get the concentration of hydroxide, which you get a value, a result of 5 10 to the power minus 7. 5 10 to the power minus 7. That's how we can calculate the concentration of the hydroxide, hydronium and base. Another question, guys, the question 5 in the section review. Arrange the following solution in order from lowest to highest pH. Lowest to highest pH means the smallest to the highest. 0.0 10 molarity of HCl, and then 0.10 molarity of H2SO4, and then 0.10 molarity of HF. Guys, you know that the HCl produce 1 hydronium, is complete strong acid, but H2SO4 produces 2 hydronium per molecule. So the pH of this is lower than the HCl, and then HCl lower than the HF. So the sequence is what? H2SO4 lower than HCl, and then HCl lower than the HF. HF has the higher pH than the others. H2SO4 has the least pH. Here the relation between pH and hydronium, as we talked about, pH is inversely proportional with the hydronium and acidity. pOH is directly proportional with the hydronium and acidity, which is the solution, relation between the pH, pOH, acidity, alkalinity of the solutions, guys. For the types of questions that may be asked, let me show you a technique in order to understand on the scale 0, 7, 14. From the least pH, we can say the diprotic, strong diprotic acid, strong diprotic, and then followed by what? Strong monoprotic, monoprotic. and then weak acid, and then acidic salt, and then H2O, and then basic salt, weak bases, and strong base, 1 hydroxide, strong base, 2 hydroxide. That's the sequence if a group of compound is given. For example, let me provide a group of compounds, guys. HF, HNO3, H2O, NaOH. Which of them has the highest pH? NaOH, because strong base 1 OH, highest pH. The least pH, HNO3, strong monoprotic. Which of them has the equal amount of hydronium and hydroxide? H2O. Equal pH and pOH, H2O. Which of them has the highest hydronium concentration? HNO3. Highest hydroxide concentration, NaOH, has the highest pOH. We talked about pH. This has the least pH and the highest pOH. This the highest pH but the least pOH. That's how we can determine and answer the questions. Let me write another type of question. NS3, NaF, H2O, CS3, COOH. Among them, which one has the highest pH? This is acid, neutral, acidic salt, basic salt, base. So the base has the highest pH among them. How about it? Which of them has the pH, has the highest pH? Which of them has the least pH? The acetic acid. Which of them has the highest pOH? The acetic acid. Least pOH, the ammonia. Equal pH and pOH, H2O. That's how we can answer the questions according to the given tip which I have provided. For the strong, we talked about the strongest, how to calculate the hydronium, hydroxide, pH and pOH. How about the weaks? Guys, solution of weaks such as acetic acid present a different problem or a different issue. The hydronium cannot be calculated directly from the molar concentration because not all of the acetic acid molecule ionize it. The weak acids and weak bases, they are not completely ionizable compounds. Due to not knowing the exact degree of their ionization, the ionization degree, we are not able to calculate the hydronium and hydroxide of those groups of compounds directly. We will be able to calculate the hydronium and hydroxide by knowing the Ka and Kb values, which we will be talking about them in chapter 6. Ka represent the constant ionization of acid and the Kb represent the constant ionization of bases. If the Ka is known, that you'll be able to represent the hydronium concentration because the Ka represent the degree of ionization of the acid. If the Kb is known, you'll be able to directly convert it to the hydroxide concentration because Kb represents the hydroxide concentration. But for here, what will be the solution, guys, for solving the questions about the weak acids and weak bases? We will follow the following strategies and the notes, and we will be solving questions. For solving questions related with the weak acids and weak bases, what to do? Due to that we do not know the degree of ionization, we are unable to get an exact value of them. Follow the following procedure. The procedure must be followed. Guys, the first, if concentration of weak acid is given, if concentration of weak acid is given, we will solve by assuming as a strong acid. For the purpose of calculation, we assume it's strong acid. But for the purpose of this is for the weaks. But when we calculate the values, later we'll be providing the tips, the hydronium of the weak, the hydroxide, the pH, pOH of the weak, compared to the strong is what? How about if it is the second, guys? If concentration of weak base is given, we assume as the strong base for the purpose of calculation. Find the values by using the following ranges. Guys, let me show you for the weak acids and the weak bases as well. 0, 0, 7, 14. Guys, the region of the strong acid is in this region, strong acid. And the region of the weak acid is in this region, weak acid. If we compare the weak acid's pH to the strong acid, of course, the weak acid has a higher pH than the strong acid. If we compare its hydroxide concentration of the weak acid is higher than the strong acid. But if we compare the hydronium of the weak acid, it's lower than the strong acid. The hydronium of the weak acid, it's lower than the strong acid. And the pOH as well. pOH of weak acid is lower than the strong acid's pOH. So by using this, you'll be able to solve the questions. We assume as strongest, we derive or calculate the values as strongest, but later we have to use the ranges of values as this. For the weak acids, guys, pH, you have to use this technique. pH and hydroxide, as I told you, is higher than the calculated pH and hydroxide. pH and hydroxide of the weak is higher than the calculated for the strong, we assumed. But the pOH and hydronium is lower than the calculated pOH and hydronium. For the weak bases, guys, the weak bases, let me show you for the weak bases. 0, 7, 14. The weak bases region here, guys, is given in this region. The weak base is in this region, and the strong base in that region. The pH of weak base is lower than the strong base. So the pH and hydroxide of the weak base is lower than the calculated pH and hydroxide. But the pOH and hydronium of the weak base is higher than the strong, than the one which we calculated by assuming the strong. Let us solve a question and then we will be able to understand those notes. Find the pH, pOH, hydronium, hydroxide for the concentration of HF, which is equal to 1 10 to the power minus 4 molarity. HF is a weak acid. Then we have to apply these notes on how to calculate the hydronium, hydroxide, pH, pOH. First of all, we have to assume as a strong acid for the purpose of calculation. So assume what is it? The strong acid. When we assume as a strong acid, so directly the concentration of HF is equal to what? This is monoprotic acid, as a strong monoprotic, is equal to 1 10 to the power minus 4. This is calculated value, calculated by assuming. And then divide the 1 10 to the power minus 14, divide by 1 10 to the power minus 4, you get the hydroxide as 1 10 to the power minus 10. The pH is equal to 4 and the pOH is equal to 10. But for the HF, which is a weak acid, the results are as follow. The above results are, we assume it as strong, calculated results. But we have to for the weakest, pH of the weak is higher than that calculated pH. So the pH of the HF higher than 4. Its pOH less than 10, which we calculated pOH. The hydronium less than the 10 to the power minus 4. The hydroxide higher than 10 to the power minus 10. That's how we can solve for the weak acid. For the weak base, the same guys, the same strategy for the weak base. Concentration of the ammonia is given 1 10 to the power minus 6 molarity. So from this we can determine the hydroxide concentration 1 10 to the power minus 6 direct, and then hydronium is equal to 1 10 to the power minus 8, pH is equal to 8, pOH is equal to 6. But for the ammonia solution, the values pH of the ammonia is lower than the calculated pH, than 8, which is we calculated here. Its hydroxide is lower as well than the calculated hydroxide. Its pOH and hydronium higher than the values. So the pOH higher than 6 and the hydronium higher than 1 10 to the power minus 8, which we calculated above. That's how we can solve for the weak acids and the weak bases as well. This value, this table 5, represents the relationship between hydronium and hydroxide and pH at 25 Celsius, guys. Changing the hydronium and hydroxide is inversely proportional, and the pH as well changes with the temperature, but it's inversely with the temperature. Let us solve some ministerial exam question. That's the end of the section. A solution contains 10 to the power minus 3 HCl. What's the pOH of that solution? So the pH is equal to 3 and the pOH is equal to 11. This is the mathematical calculations can be solved. pH of calcium hydroxide is 9. Find the hydronium. The pH is 9, so hydronium is equal to 1 10 to the power minus 9. Molarity is equal to 1 10 to the power minus pH. pH of this is 9, find the hydroxide. Hydronium is equal to 10 to the power minus 9, the hydroxide is equal to 10 to the power minus 5, which is D is the correct answer. If pH of calcium hydroxide is 9, how many moles of calcium hydroxide required to prepare 2 liters of solution? Guys, this refers to what? By using CaOH by 2 dissociates to form Ca2 positive plus 2OH negative. What's the requirement? How many moles of required calcium hydroxide to prepare 2 liters solution? Guys, the molarity is equal to what? Mole per liter. If we how to calculate the mole? Mole is equal to molarity multiply liter. The liter is given 2 liters. But how to calculate the concentration of calcium hydroxide? Through the given pH. So the pH can be used to calculate the hydronium. Hydronium is equal to 1 10 to the power minus 9. The hydroxide is equal to 1 10 to the power minus 5. Okay. This is the concentration of hydroxide. To find the concentration of calcium hydroxide, hydroxide is twice as the calcium hydroxide. So we have to divide this by 2. You get 0.5 10 to the power minus 5 or 5 10 to the power minus 6. That's how we can determine the concentration of what? We calculate the concentration of CaOH by 2. As the concentration is calculated, 5 10 to the power minus 6 multiplied 2 liters is equal to 10 10 to the power minus 6. But 10 cannot be written as because the decimal here should be in between 0 till 9. We have to move the decimal to the left and increase the power. So it will be 1 10 to the power minus 5. Which one is the correct answer? D is the correct answer. Solution of HNO3 has a pH of 2.7, concentration of hydroxide ion equals. So this can be converted to the hydronium and then hydronium to hydroxide by Kw. Which of the following solutions contain highest concentration of hydronium? Highest concentration of hydronium. HCl, HF, CS3CWH, NaCl. Of course, highest concentration of hydronium, the strong acid. A is the correct answer. pH of a solution is 8 point molar concentration of this. So the pH can be converted to the hydronium to hydroxide. The hydroxide divided by 2, you will get the concentration of calcium hydroxide. Which of the following pH value represents the highest acidity? Highest acidity means the least pH, so pH of 1. Given the hydroxide of a solution 1 10 to the power minus 11, the solution is 1. So the hydroxide is lower than 10 to the power minus 7, that means it's the acidic solution. The value of 10 to the power minus 5 KOH solution equals to what? The pH value. So the 10 to the power minus 5 is the hydroxide. 10 to the power minus 9 will be the hydronium, and then 9 will be the pH. Which of the following is always true for aqueous solution of acids? The hydronium concentration higher than the hydroxide? Yes. pH higher than the POH? No. Hydronium equals 1 10 to the power minus 7? No. pH equal to 7? No. So A is the correct answer. At the power of the hydrogen pH is given. What's the concentration of hydroxide ion? Can be converted to hydronium and then to hydroxide as well. If we know pH of a strong acid solution, we'll calculate molar concentration, hydronium, hydroxide, all of them can be calculated. That's the types of the questions, all the types of the questions, multiple choices, are easy. Which of the following solution would contain the highest concentration of hydronium? Highest concentration of hydronium, H3PO4, HCl, H2SO4, HNO3. So the H2SO4 has the highest concentration of hydronium. B is the correct answer. Which of the following shows a solution that possesses a pH greater than 7? pH greater than 7. pH greater than 7, that means alkaline. Hydronium higher than 10 to the power minus 7, it's acidic. Hydronium higher than the hydroxide is acidic. Hydronium less than hydroxide is basic. POH 11 is acidic. So C is the correct answer. Which of the following